Hello and welcome to The Explainer, where we're digging into a really fascinating mystery from the world of complex dynamics. So let's get right to it. In complex dynamics, there's this universal constant, Feigenbaum's delta, and it predicts a really important singularity. But here's the question. What happens if you just tweak the rules a tiny bit? Did that singularity just move somewhere else, or did it vanish completely? That's the exact question paper 27 of the Non-Holomorphic Fractal series sets out to answer. Okay, so on the one hand, you've got your standard, well-behaved holomorphic case. This is our baseline. And here, the Feigenbaum singularity is a known landmark, right where it's supposed to be. But on the other hand, you have this thing called the bird map. It's got this one tiny non-holomorphic tweak, and what previous papers found was, boof, the singularity was just gone. They called this outcome B. So this right here, this is the map at the very heart of our mystery. And you see that little g eta term? The one that depends on the imaginary part of z? That's it. That's the whole game. It might look small, but it's the crucial change from the standard holomorphic world. It's the little tweak that breaks all the usual rules. Right, so how do you actually prove that something isn't there? Well, to solve this puzzle, paper 27 pulls out a really powerful analytic tool, something that lets us measure the growth rate of the system's coefficients. This is our first big clue. The investigation follows a pretty clear path. Think of it like this. First, you take the behavior of the bird map and you encode it into a long sequence of numbers, our coefficients. Then you use those coefficients to build a special function, the Gamma-Borel transform. The key to everything is figuring out the safe zone for this function, which is all determined by its radius of convergence. And that brings us to the hero of our story, exponential type. It's really just a single number that tells you how fast those coefficients are growing. But here's the magic trick. If you take the reciprocal of that number, it gives you the radius of a disk. And inside that disk, our function is guaranteed to be totally well-behaved. It's analytic, no surprises, and absolutely no singularities. Okay, so with that tool in hand, we get to the core analytic argument of the paper. This is it. This is the smoking gun that really cracks the case of the missing singularity. Now, it turns out the Birkhoff map has this one really special property that just unlocks the whole problem. The imaginary part of the orbit kind of does its own thing. It evolves independently. And it's ergodic, which is a fancy way of saying that over time, it explores all its available space pretty evenly. Because of that, we can use Birkhoff-ergodic theorem to calculate the exact long-term average behavior of the system. And when you do that calculation, you get this, a specific constant value for the exponential type, roughly 0.0942. And here's the kicker. This value holds true as long as that little non-holomorphic term, epsilon, is switched on. It doesn't matter how small it is. If it's not 0, this is the number you get. So now for the moment of truth. We just have to compare our new value to the known location of the Feigenbaum singularity. What do we see? We've got 0.0942 versus 0.2142. It's not even close. Our exponential type is way, way smaller. And this is where it all comes together. Remember how the reciprocal of the exponential type gives us that safe zone disk? Well, because our number is 0.0942, the radius of that disk is its reciprocal, which is about 10.53. I mean, that is a huge disk of convergence. Think about it. A singularity, by its very definition, has to live on the edge of this disk. But where's our Feigenbaum point? At 0.2142. It's not on the boundary at 10.53. It's deep inside the safe harbor. So it simply cannot be a singularity. And there you have it. That's the analytic proof that it's been completely destroyed. Okay, so that's the pure math. But you know, any proof that relies on ergodic theory, which is all about infinite time averages, really needs a reality check. So let's look at the numerical evidence, which acts like guardrails for our theory. First up, they run this really tough stress test based on the law of the iterated logarithm, or LIL. It's designed to see if the random-looking fluctuations in the orbit stay within the bounds that theory predicts they should. The results? They ran 500 long simulations and got 0 violations, a perfect score. And this isn't just about getting a nice number. This is a critical guardrail. It gives us a ton of confidence that the deep mathematical assumptions we made for the proof actually hold true for the real-world computations we're running. All right, next up, the researchers go hunting for approximate singularities using a technique to find what are called Pade poles. In the standard case, when epsilon is 0, these poles are exactly where you'd expect. But watch what happens when you flip that epsilon switch on. I mean, even for a ridiculously tiny perturbation, bam, there's this massive, instantaneous jump. The poles are flung far, far away. And when you visualize it, the story is just incredibly stark. It's a completely binary situation, at least the resolutions they tested. The poles are either sitting right on top of the Feigenbaum spot when epsilon is 0, or they are launched into deep space for any non-zero epsilon. There's no middle ground here. And what's really amazing is that this isn't some chaotic mess. The poles land in a very specific, highly structured place the paper calls a distance floor. The location of these now distant poles is super stable, which is just more proof that the singularity isn't just hiding nearby. No, it's been actively repelled to a new, stable home. So let's put it all together. What's the final verdict when we combine the airtight analytic proof with these rock-solid numerical guardrails? What we have is a totally conclusive case built on 3 main pillars. First, the analytic proof, which shows destruction is a mathematical necessity. Second, the little check, which confirms the system is well behaved enough for that proof to apply. And third, the distance floor, which gives us clear, direct numerical evidence you can see the destruction in action. And that really is the final verdict of paper 27. The mystery is solved. The paper doesn't just say the singularity is gone. It provides a constructive mechanism that explains why it vanishes entirely. And that leaves us with a really fascinating final thought. What does it actually mean when a constant we think of as universal can just be switched off by the absolute smallest, most subtle change to the rules? It really makes you think about that delicate, razor-thin line between a universal law and the absolutely pristine conditions that allow it to exist in the first place.